Good morning, everybody. I just thought I'd make this screencast to sort of address the information that's in the advanced information supplied by CCEA. But as you already know, you do have to revise everything that is in the specification. But I just thought I would make this to sort of focus that revision over the weekend and sort of clear up any misconceptions or any questions that you may have. So as I said, I'm going to go through every topic here and sort of pick out little bits of information from the advanced information, and hopefully that will support your revision over the weekend. So the first thing is all about atomic structure, and the whole idea is that in an atom, the atomic number, which is the smaller number we can see here for 9 for fluorine, tells us the number of protons in an atom. So it also talks about the fact that overall atoms are electrically neutral, so they have no electrical charge, and that's because we know that there are the same number of positive protons, which there's 9 in this case, and negative electrons. Okay, so plus 9 minus 9 overall would be 0 for an atom. Now, to find out the number of neutrons, you simply take the atomic number, which is the smaller number, away from the bigger number. So in this case, it would be 19 minus 9, which gives us 10 neutrons. If we're talking about ions, remember what an ion is. It's a charged particle formed when an atom either loses or gains an electron. Now, I always talk about, if you think about it, an electron is negatively charged. So if you lose something that is negative, you are becoming more positive. So if you have a positively charged ion, there is more positive protons than negative electrons. So let's say you have Na+. You look at the number of protons in the atom and you take away 1, and that will give you the value of the number of electrons in the ion. But if you have a negatively charged ion, that means that you're gaining a negative electron. You're going to have 1 more electron, or however more electrons in the ion than you would in that particular atom. So for example, with chlorine there are 17 protons, but in the Cl- ion there are 18 electrons, so therefore a minus charge. So if we have a look at this past paper, we have here aluminium 3+. If you look at aluminium and we look at the number of protons, that's the atomic number, you'll see that it's 13. However, the number of electrons in this example is 10. So there are 13 positive protons, 10 negative electrons, so therefore the charge is Al3+. The number of neutrons stays the same, which is 14, because 13 plus 14 is 27. If we have a look at the next one, it says the number of protons is 8, and if you go to your periodic table, the only element that has 8 protons is oxygen. However, there are 2 more negative electrons than protons, so therefore the charge of the oxide ion is O2-. And the mass number is obviously the number of protons plus the number of neutrons, which is going to be 16. Br-, the number of protons is 35, but you see there that it has a minus charge, so you add 1 on and you get 36 electrons. The relative atomic mass, the definition needs to be learnt off. It's the average mass of an atom, of an element, relative to 1/12 of the mass of an atom of carbon-12, which has a mass of exactly 12.000 grams. Now that is a real waffly definition, but it does need to be learnt off because it can be asked as a definition, or you have to fill in the blanks. So to work out the relative atomic mass, it's the mass number times abundance plus mass number times abundance divided by total abundance. So if we look at this example here, it has 2 isotopes of thallium, mass number 203, mass number 205. So if we were then going to work out the relative atomic mass of a thallium atom, you would do 203 times 30 plus 205 times 70 divided by 70 plus 30, and you get a value there of 204.4. Moving on to bonding, the first type of bonding is ionic bonding, and this occurs between ions. Obviously it's stated in the name, and this occurs between metals and non-metals. The metal is responsible for transferring its electrons from the outer shell to a non-metal, and if you're losing electrons, it then becomes positively charged, which is a cation. On the other hand, non-metals gain electrons and become negatively charged, and they are called anions. And ionic bonding, they're held together by opposite charges, and that's called electrostatic forces of attraction. So here we have an example of the magnesium atom, which has 2 electrons in its outer shell, transferring its electrons to an oxygen atom. And you can see here over on the right hand side that oxygen then becomes 2- because it has gained 2 electrons, whereas the magnesium ion has a 2+ charge because it has lost 2 electrons. What structures does it form? Well, ionic bonds then build up to form what we call giant ionic lattices, and here we have a structure of sodium chloride. So ionic compounds form giant lattices, with each ion being surrounded by ions of opposite charge. So you can see here there would be sodium ions in green, which are surrounded by chloride ions then in the purple. And a giant ionic lattice is three-dimensional, and it has a structure of oppositely charged ions held together by ionic bonds. When we're talking about the properties, that's words to describe an ionic lattice. Well, you always think about your salt. It's soluble in water. It can conduct electricity when molten or dissolved, as the ions are free to move and carry charge, but they're not able to do that when they are a solid. So that's important. They can only conduct when they are molten or dissolved because the ions are free, but can't do it when they are solid. They also have high melting and boiling points because there are strong ionic bonds between the ions, which require a lot of amounts of energy to break. Next up then we have covalent bonding, and this is the type of bonding which occurs between nonmetals. It involves the sharing of electrons between atoms. When you're thinking about covalent bonding, you should be thinking about overlapping circles, dot and cross diagrams. And some definitions in there you should be thinking of is a molecule is two or more atoms covalently bonded together. And that term diatomic, di meaning two, atom meaning atom, means that there are two atoms covalently bonded in a molecule. So things like H2, O2, CO2, Cl2, etc. So how would you draw that? Well, you can either draw it with your circles or you can leave the circles out, but there must be a shared pair of electrons between the two atoms. So you can see here chlorine, for example, has 7 electrons in its outer shell, so it overlaps with another chlorine with another 7 electrons, and now each of those have 8 electrons in their outer shell. In the example of hydrogen chloride, hydrogen can only possess 2 electrons because it only has one shell, so therefore they are both full. Well, covalent structures then can either form molecular covalent or they can form giant covalent structures. Molecular covalent is all about small molecules. So all covalent structures apart from diamond, graphite and graphene form molecular covalent structures because they are small. They have weak van der Waals forces between the molecules, which means that they require little amounts of energy to separate and therefore have low melting and boiling points. Molecular covalent structures are also generally insoluble in water, and they do not conduct electricity because they do not have any free ions or electrons to move and carry the charge. So how would that look? For example, if we had lots of carbon dioxide molecules, we know that there are strong covalent bonds between the atoms, but between the molecules we have weak intermolecular forces called van der Waals, which require little amount of energy to separate. Moving on then, we're talking about the term alloy, okay? And an alloy is a mixture of two or more elements, one of which is a metal, and overall the structure has metallic properties. So if you think about steel as a mixture of iron, which is a metal, and carbon, but overall the property of the steel alloy is that it has a high melting and boiling point, strong, and it conducts electricity. And the purpose of that is, if you think about this diagram here on the left, that would be lots of different metal cations. But if you put in another element there, it means that the ions are not able to move over each other and be malleable and ductile. Alright, so they have a high tensile strength. Moving on then to talk about how we write chemical formulae. So it's really important that you use whatever method that you're comfortable with, but the one I would recommend is the swap and drop method for writing chemical formulae. So you look at the valency or the charge of either the group that the atom is in. So for example, if it's in group 1, it has a valency of 1, group 7, it has a valency of 1, and so on. Or the molecular ion, which you will find on the back of your formula sheet. So if we have a look here at the sulfate ion, which is SO4 with a charge of 2-, that 2- means that the valency would be 2. So if we have a look at an example, write the formula of aluminium nitrate. So aluminium is an atom found in group 3, so its valency is 3. Nitrate is a molecular ion which has a charge of 1-, so we put 1 underneath the nitrate ion. So we swap and drop 1 aluminium and 3 nitrate, and therefore the formula becomes 3 AlNO3 3. And please notice that there are brackets outside NO3 with a 3 outside the bracket because there are 3 nitrate ions. Ionic equations then, these only involve ions, so you should have plus charges and negative charges, and a very common one is the ionic equation for the neutralisation reaction. So hydrogen ions, aqueous, react with aqueous hydroxide ions from your alkali to form liquid water. So if you have here, it says sodium hydroxide and hydrochloric acid react to form sodium chloride and water. Use this equation to help write an ionic equation for the formation of sodium chloride. So the charge of the sodium ion in sodium hydroxide would be Na+. The charge of the chloride ion in hydrochloric acid is Cl-, which react together to form Na+ plus Cl- to give NaCl. Half equations then, you should be thinking about these must involve electrons. So half equations, it's not a full equation, it's a half equation. So if we think about here, chlorine is an element in group 7, so therefore it has 7 electrons in its outer shell. It needs 1 electron to become Cl-. The chlorine molecule needs 2 electrons to become 2 Cl-. Sodium is in group 1, it loses 1 electron to become Na+, plus an electron. Looking at the composition of the periodic table, we should be thinking about our groups go 1, 2, 3, 4, 5, 6, 7 and 0. Group 1 is the alkali metals, Group 2, alkaline earth metals, Group 7, halogens, Group 0, the noble gases. When we're thinking about which ones are solids, liquids and gases, there are only 2 liquids on the periodic table, denoted in yellow, mercury and bromine. We have the gases that are represented in pink, hydrogen, nitrogen, oxygen, fluorine, chlorine, helium, neon, argon, krypton, xenon and radon. The rest are considered solids. Looking at our halogens then, which is found in group 7, colours of the halogens and the physical state. Fluorine is a yellow gas, chlorine a yellow-green gas, bromine is a red-brown liquid, and iodine is a grey-black solid, but when you heat it or sublime iodine, it turns into a purple vapour. So look that you're noticing as you go down the group, they become darker, and they're progressively going from a gas to a liquid to a solid. Note that all of the halogens form diatomic molecules, so F2, Cl2, Br2, I2. Sometimes you're asked to predict the colour of astatine, which would be a black solid. As you go down the group, if they become less toxic, so fluorine is the most toxic halogen, and the reactivity also decreases as you go down the group. So fluorine is more reactive than chlorine, which is more reactive than bromine. And we can see this by carrying out the displacement reactions of the halogens, where a more reactive one can displace a less reactive one from its compound. So you can see here, chlorine will displace bromide to form bromine, and look at your colour changes to form an orange solution for bromine. Chlorine will displace iodide to form a brown solution as iodine is given out. Bromine will only displace iodide to form iodine, and iodine cannot displace anything because it is lower down in the reactivity of the halogens. Our transition metals are the big block that are found in the middle between groups 2 and 3, and they react to form ions with different charges. So we talk about group 1 form 1+ charges, group 2, 2+, etc. However, the transition metals form a variety of charges. They generally form coloured compounds, whereas group 1, group 2, aluminium and zinc compounds are all white. Moving on to quantitative chemistry, if you're looking to work out the relative formula mass or the MR of a compound, you have to look at the individual atoms that are present in that particular compound. So if there are brackets, so you can see here, this is the iron sulfate. There's a 3 outside the bracket, so that means that you multiply 3 by everything inside. So that would be 2 irons, which is 112, 3 times sulfur, which is 96, 12, 4 times 3 oxygens, which is 192. Add all of those together and you get 400. If you're asked to work out the percentage by mass in a compound, you look at how many of that particular element that there are in the compound and divide by the total MR of that compound. So for example, find the percentage of calcium in calcium fluoride. So there is one calcium which has a relative formula mass of 40. Calcium fluoride has an overall relative formula mass of 78. So 40 divided by 78 multiplied by 100 is 51.3%. Moving on then to look at working out reacting masses and limiting reactants. So you use your Mr. tables. So you down the side of your page you'll write MR, which stands for mass, relative formula mass, moles, ratio. And don't forget your moles triangle. Moles is equal to mass divided by formula mass. Fill in all of your values and work out those calculations. Have a look back in your booklets to refresh that and complete past paper questions. Moving on to percentage yield. So percentage yield, we talked about this. How do you work it out? Well, you look at what you actually obtained in the reaction and divide it by what you should have got from your molar calculation and multiply that by 100. So, for example, if you had a yield of 5 grams, but you were expecting 10 grams, 5 divided by 10 multiplied by 100 would give you a value of 100%. If you are asked to state why the percentage yield was less than expected, you're talking about there is a loss of the reactants through transfer, reaction didn't go to completion, or there were side reactions that were taking place. When we're talking about acids and alkalis, all acids dissolve in water to produce hydrogen ions H+, whereas alkalis dissolve in water to produce hydroxide ions OH-. Strong acids and alkalis fully ionize in water, keyword fully, whereas weak acids only partially ionize in water. And if we're thinking about a neutralisation reaction, this is the reaction between an acid with hydrogen ions and an alkali, which is a soluble base. So H plus OH minus to give you water. And please note your state symbols is aqueous, and liquid water. This is a 3-mark question which is asked very, very often, and students very underperform in it in exams. So it's worth your while learning that equation off. So if we have a think here, HCl, NaOH forms NaCl in water. So in this diagram on the left, your orange particle is your hydrogen ion. On the right hand side, the grey and orange is your hydroxide ion. They're joining together to form a molecule of water. Reactions of your acids, remember MASH, metal plus acid, salt plus hydrogen. A big salty wave, so if you have an acid plus a base, gives you salt plus water. Sulfuric acid reacts with sodium hydroxide to form sodium sulfate plus water. If you have a carbonate, a crazy salty wave crashes down. An acid reacts with a metal carbonate to form a metal salt plus water plus carbon dioxide. And if you're asked to test for carbon dioxide gas, you bubble it through lime water and you're going to get that milky colour. Colours of your salts, as mentioned before, all of your group 1, group 2, zinc and aluminium salts are white and they dissolve in water to form colourless solutions. However, your transition metal compounds are all coloured, and in particular you need to know the colours of your coppers. So copper is this red brown shiny metal, but if you have copper oxide, that would be D, which is a black powder. Copper carbonate is a green powder, anhydrous copper sulfate is white, and hydrated copper sulfate over here, C, is a blue powder or crystal. It is worth noting that all of your copper compounds dissolve in water to form a blue solution. So even though this is green powder and black powder, they dissolve in water to form a blue solution. Pure substances, things like gold, copper, sugar, salt. What is it? It's a single element or compound without anything else mixed in. So you can have pure hydrogen, pure diamond, pure copper. When we're thinking about pure and impure substances, if something is pure, it will have a very specific melting and boiling point. For example, pure water has a boiling point of 100 degrees Celsius, whereas impure substances have a range of melting and boiling points. So if you have a think about here, this graph on the left hand side shows us a pure substance. It has a definite boiling point, as you can see by the straight line on the graph, whereas a mixture has a range of boiling points and you can't really decide what the definite one is. Formulation was also in there, and that means that is a mixture that has been designed as a useful product and is formed by mixing together several different substances in carefully measured quantities to ensure the product has required properties. That's a wordy definition, but it does need learnt off, and they can ask you to apply your knowledge to different formulations, but we're going to talk about ones that you should know. So ones that you can have is alloys. We talked about this earlier. It's a mixture of two or more substances, one of which is a metal. The one in the middle here is a fertilizer, which is a mixture of nitrogen, phosphorus and potassium compounds. And the one on the right, I'm sure a lot of you have had this before, which is Calpol, comes under the term of medicines, as it is a mixture of active drug, such as paracetamol, and flavourings and sugars, etc. And the final thing that I'm going to leave on today is the chemical test for water. If you need to test an unknown liquid for water, which is colourless, we use anhydrous copper 2 sulfate. If the substance is water, it will turn from white to blue. And you can see there on the watch glass we have white powder, which is anhydrous copper sulfate. And if the liquid that you're adding is water, it will turn from white to blue. So guys, hopefully that was useful for you, and I wish you all the luck in your exam on Monday. And if there are any questions, please don't hesitate to let me know. But as I said, keep that revision going, cover all grounds, but hopefully this will focus your revision over the weekend.